Good evening, all. Welcome to the second week session of Fundamentals of Convective Heat Transfer course. So this week we will be discussing on three different topics. One is on the derivation of energy equation using Reynolds transport theorem. There are other ways to derive the same thing, but we'll be using Reynolds transport theorem as discussed in the lecture videos, followed by derivation of boundary layer equation. When I say boundary layer equation, it just means the hydrodynamics. So by default, if you do not specify whatever it is, so it would be hydrodynamic boundary layer equation, followed by the boundary layer energy equation. So with that, after this, we'll solve some problems. Most of these problems will be based on the derivation of these equations and a few scaling analysis. In the boundary layer equation, we'll also discuss something called scaling, which is often useful at times where, instead of solving the complete problem, we'll have a rough estimate of what to expect from the solution. So that is where the scaling analysis comes into picture. We'll also see the application of that in one example in one of the solved problems. Okay, let us get started then. So the first concept here is the derivation of energy equation using Reynolds transport theorem. As you might already be familiar with the Reynolds transport theorem, it states that the rate of change of any property where n is an extensive property in a system equals the rate of change within the CV and whatever is coming in and out, going out. So basically, to put in simple words, whatever is happening within the system, like if the delta t goes to zero, this entire boundary, whichever is a control surface boundary, can be taken to be the system boundary, where system is an identified collection of particles. So when we have such a kind of a system, then the rate of change of property of that particular system is given by whatever is changing within the system plus whatever is going out minus whatever is going in. So when we write this integral over control surface with an n cap that is pointing outwards, outward n cap is positive. So whatever is going out is considered to be positive and whatever is coming in is considered to be negative. So you can think of this in a very simple way where you have, for example, you need to find the total the number of people in a particular country or something. All we need to do is this is the rate with how much is changing within the CV, which is basically the number of births and deaths that will come inside this particular term. And this is whatever is crossing the border. So whoever is coming into the country through this particular border and whoever is going out. If you can account for all of these changes, then we'll be able to know what is the rate of change of population within that particular country. So that is a simple idea for Reynolds transport theorem. So now we are trying to use that particular theorem in the case of an energy equation, where in case of energy equation, this capital N is an extensive property and the eta over here is an intensive property. So extensive is one which depends on the amount of matter, whereas intensive doesn't depend on the amount of matter. So the total energy is what is conserved. So the energy is a combination of both the thermal energy followed by the kinetic energy. We have not included the potential energy as of now. In most of the cases that we will be discussing, it will be more or less negligible. So even if not, we will see that how to include that a little later. But for now, let's see, it will be included in a different way, which we will discuss later. Now, when we have the kinetic energy and the thermal energy, if we substitute that equation into this into the Reynolds transport theorem, we have the total energy dEdt of the system given by whatever is changing, the rate of change within the CV followed by whatever is going and coming in. And here, if you see, there is VR, and here we changed it to V. And the other thing you need to notice is the time derivative applying outside the integral has been shifted to inside the integral. So this particular thing can be done only under the following assumption, where you have a stationary and non-deformable CV. When the non-deformable CV implies the volume of the CV is constant. So if the volume is constant, then the derivative can be taken inside the integral. And we are saying it is a stationary, so there is no relative velocity. The relative velocity will be equal to the actual velocity of that particular of the actual velocity. there is no velocity with respect to CV. So, or we are essentially saying the velocity of the control volume is 0. So in that particular scenario, we have this equation, the original equation getting reduced to this form. Now we can always apply, so the idea here, now we have one term with respect to volume integral, and then we have a surface integral. So we aim to convert both of them into volume integral so that we can come up with a differential form of this particular governing equation. So this particular form is called an integral form, because in this, all we are caring about is what is happening in a very big control volume. But what we are interested in is coming up with a differential form where we can apply this and come up with a differential form wherein you take a small control volume dV, I mean a smaller volume dV like this, and we are trying to find what are the governing laws or governing equations in this particular dV. So if we can find that, then all we can do is solve for that particular dV, like we can consider this dV anywhere within the control volume, and we'll be able to solve for that particular equation. That is the whole aim of this particular approach. So in order to do that, we need to convert everything into a single form. So this surface integral we'll have to convert into the volume integral, for which we'll use the Gauss divergence theorem, where you have f dot n cap is del dot f dv, where the surface integral and volume integral are related in this particular way. Once you apply that, you can bring both the terms together under one integral, under the volume integral, where you have the rate of change of the energy plus the divergence term of the energy and given by this velocity. So this term will tell you how much is going out when it's coming in. Basically, the net flux outside, the net flux leaving the particular dV volume, and this particular term is basically whatever is happening inside the dV. But as you can see, we can always expand this particular derivative. So we can expand this particular term. So if you just apply the chain rule, the first term will be rho times del E del T plus E times del rho del T, followed by the same if you do for the chain rule for the hi. I'm just going through a quick summary of the derivations first, followed by we'll take up on problems as well. Yeah. So you can group the terms together, one with respect to the energy terms, and then the other has the continuity equation. When that particular term goes off to 0, because we are from the continuity equation, so then we'll have the net energy change with respect to system is given by this particular expression over here. So here we have a term that is the transient term, followed by this is our advection term. This is something similar which you have seen even in the momentum equation, where instead of E we'll be having the momentum term. But now, as you see, the main problem with this equation is the equation has E in it, which is something that we do not know from the flow properties. Velocity is something that we know from the flow, but this E is something that we do not know. So we want to kind of express this E in terms of the properties that we can measure, like temperature, pressure, and velocity. So it needs further elaboration. That's where the other steps come into picture. So first, on the LHS side, we have dE dt of the system, which is given by, from the first law of thermodynamics, we know that is Q dot minus W dot, where Q dot is the net heat transferred to the system, and W dot is the net work done by the system. So this is positive when it is work done by the system, and this is positive when you give heat to the system, as given by this particular arrows. Now, under the scenario when delta T tends to 0, so basically if you recall the derivation of Reynolds transport theorem, we start out with a particular system and CV being identical to each other, and then we'll try to offset the CV after time t plus delta T, and then we will see what is happening in this region. That's how we derived the Reynolds transport theorem. So when that particular delta T tends to 0, both the system and CV are identical to each other. So that's when we have Q dot system equal to Q dot CV and W dot system equals to W dot CV. We can substitute that. But again, as we see, this Q dot and W dot are again in something that we do not measure directly. So if we know these terms directly, then we can get the integral form, but still we need to be able to find in a differential form where I can, if I arbitrarily consider a small volume inside this, I am trying to get an equation for this, which we cannot do directly in this particular way. So we are trying to express this again in terms of the properties that are locally dependent here. So we need to expand these terms further. So then first we start with the heat transfer term, where the Q dot CV is basically the net heat inside the CV, inside this particular dV. Again, as I said before, anything within this can be decomposed into two things. One, what is happening inside, and what is happening at the boundaries. Those are the two things that you always care about. So basically, whenever you have a system, is basically whatever is inside the system and whatever is happening at the boundaries. It's always the two components. So the first component is whatever is happening inside. We are denoting it with, since it is anything inside is a volumetric thing. So this is the internal heat generation for a volumetric quantity, and then whatever is happening at the surface is given by the surface heat flux. So this is basically the net heat flux that will be leaving from the surface. So if this is my entire CV, so this particular term we are showing the integral over the entire control surface. So over the entire control surface, this is my boundary. So on this boundary, whatever is the heat flux. So if you are considering a small volume, and then you should be considering the heat flux at that particular boundary of that particular small volume element that you will be considering. Again, one of them is a volume integral and surface integral. So we want to convert everything into volume integral, use a Gauss divergence theorem. So this is the equation we have. A quick question over here. So we have two terms here. So there should be some difference between what is Q triple prime, which is basically the internal heat generation due to internal heat addition due to internal generation, and then this is the surface heat flux. So just to understand whether these two terms are clear. So consider these two cases where you have an electric vehicle battery that is cooling. So you are driving an electric bike or something, and then that particular battery is getting cooled because of the airflow. If you are in a car or something electric car, then you'll have a separate cooling system to cool that particular vehicle. So do these both terms exist in that particular case when I'm cooling it? So if you consider the electric bike, an Ola bike or any other bike, so the air flowing against the battery will cool the battery. So which of these two terms are existing in that particular case? So if you try to cool the battery, so at the surface, on the surface of the battery or whatever is that covering the battery, there will be a net heat transfer because of convection. So you can use H times delta T. That will give you the Q double prime. So that is basically whatever is the heat that is leaving because of the surface. And then why are we trying to cool it? Because battery is getting heated up because of some chemical reaction inside. So in order to be able to find this Q dot CV, we need to know what reactions are happening inside and what is what is the net heat generation inside the battery. And for that, this Q triple prime is something that is for which you need to know the internal chemical reactions of the battery. So if you would know those particular terms, then you can calculate this Q triple prime. And Q double prime is again the heat flux on the surface, basically on the boundary of whatever CV you are considering. And that is where our convection comes, where if you know the heat transfer coefficient, you can multiply H times T minus T infinity, T surface minus T infinity to calculate that. But in more complex scenarios, you might require some other additional approaches. But eventually, one thing is you have a heat generation as well as you have both Q triple prime and Q double prime here. Consider a second scenario where you have the window of an automobile. But here, as you see, the heat generation is happening purely because of internal chemical reaction. That's why you have Q triple prime. Now, in the second example, let's say you are in a car and then you have the window that is exposed to solar radiation. And my object of interest or my particular CV is just the window. So which of these two terms do you think are present in that particular case? So it's like you have a car window and then you have some solar radiation falling on it. And my object of interest is only this particular window. The window will be getting heated up. So can I consider this as volumetric heat generation? The question clear? If you're saying something, then I'm not able to hear you. Yeah, now I can hear you. Yeah, let's say I have a window, a car window or something, which is exposed to solar radiation, and I want to apply the net heat transfer over this particular CV, where my control volume is basically the window. So this is my control surface, is the window surface, and the volume is basically the entire glass is my control volume. So in that particular scenario, which of these two terms do I have? Like, do I have both the internal generation and QW prime, or just one of them? Is the question clear? Yeah. So what do you think? Both will be present or only one? Only one. Okay. So you don't think, so you think Q triple prime is present, or which one is present? Which one of these two is present? I mean, is there internal heat generation or just the surface one? Surface will always be there because there is radiation. So I think this is clear. What about the internal heat generation? It depends on the type of glass and stuff. So if you are already familiar with the, so as the sun rays fall on the surface of the glass is not 100% reflecting. If the glass is not, usually that's the case, the glass is not 100% reflecting. So what happens is a portion of the incident radiation will get absorbed into the glass, and that absorbed radiation is something that has to be accounted for. It's like if you just consider the surface heat transfer. So basically, if you know the heat transfer coefficient here and top and bottom, you will not be able to calculate the net CV because there is a heat addition because of solar radiation, which will eventually get absorbed into it, and that will also get dissipated outside. So if you consider just the glass surface, it's as if like this is my glass. Some heat is going out, some heat is going out on all the sides. But then there is some internal generation, but this generation is because whatever is incident from solar radiation, a part of it is getting absorbed into the glass. And that will be the net heat generation that will be added. So there is like, it depends on, in your case, if in your particular case, when solar radiation is very high, then the amount of absorbed radiation, if the alpha is absorption coefficient of that glass is very high, then you have to account for this term to calculate the net heat addition. But if it so happens that you have a very highly reflecting glasses, like mirrors or something, where alpha is very less, in that particular case, you just have to consider this Q double prime, and Q triple prime, you can consider that to be zero. Is that clear? Got it? Okay. Yeah. Now this is only with respect to the first term. So we have two terms in our energy equation, Q dot CV and W dot CV. Now coming to the next term, W dot Cv is basically the rate of work done. Whenever we have work done, it's basically the rate of work done is power, that is force times velocity. So we have two different kinds of forces. One is a body force, which is happening within the volume, and then we have surface forces, which is because of some traction vector. Traction vector is basically the forces acting on the surface, like some stress or something, whatever is acting on the surface. Because of those forces, also some work will be done. These two have to be accounted to calculate my work done. And as you see, like these traction forces are again doing work on the control volume. From our original convention, work done is positive if it is done by the system. So this traction force is doing work on the particular system or whatever on the particular control volume. So this work is negative. So we're denoting minus W dot CV as the net rate of work, which is basically force times velocity. The body force, let's say, is B. Body force is like your weight, and weight is one kind of body force. If you have a buoyancy force, that is also a body force. For example, if you have an object suspended in, say, magnetic field or something, then the force will be acting throughout the volume. If there is any force which is acting throughout the volume, then you will consider that a body force. So if you have some supermagnetic fluid or something where the body will act, some kind of fields where electric fields, charged particle where you have an electric field that is influencing throughout the volume, then all those things should be considered in the body force. And anything that acts only on the surface, like contact forces, will be considered as the traction vectors, traction vector. So you just multiply that with the velocity of whatever is the fluid or whatever is that particular thing that is moving out. So that will give you the rate of work done on the system. So here we have to, again, as I said before, we want everything in terms of volume integral. We'll again apply the this particular force again. This particular term here is not directly, we cannot apply Gauss divergence directly. So we need it to be in a different form. So what we try to do here is introduce another tensor, tau double bar. So basically I'm using double arrow to say that this is tensor and not a vector. So basically it has, in 3D, it will have 9 components, whereas a vector will have only 3 components. So this particular tensor is like your stress tensor. This is related to the traction vector to this particular equation, where the tau dot n cap will give you a particular force in that particular direction. You can refer to any of the strength of materials books to get a better idea of what this particular traction vector is. But in fluid mechanics, so the idea is the stress times that particular normal direction will give you the force along that particular normal. So again, once we have this, we can apply the Gauss divergence theorem. So this is basically del dot v a. So it's some vector times a. So we apply the divergence of this particular vector. Again, a dot product of a tensor with a vector will be a vector. Like if you have 2 vectors, then we'll get a scalar. When I have a tensor with a vector, we'll get a vector. So these 2 terms, again, since both are volume integrals, I can club the terms together. This is a net equation I have. So I have W dot Cv in terms of B, tau and B. But again, we do not, B is something that is body force, which is something external. So like gravity or something which will always be given to you. But what about this tau is something that we do not know. Tau is like a tensor, but if we can relate it in terms of the other flow properties, then the entire equation is something that we will be able to solve. Currently in this form, we will not be able to do anything further. So now we take all the equations together. So this is the total equation, which is on the control volume side equals to Q dot Cv minus W dot Cv. We take terms from the previous equations, and if we club them together, so this is the net equation we have. So this entire integral term within the brackets times dv equal to 0. So we are saying integration of some particular function equals to 0. And we are saying that this should happen for any arbitrary dv that I have taken. So in my previous case, this dv I have taken here, even if I take it here or any other place, that particular equation has to be true, which means this particular integral has to be 0. That will happen only if this particular, whatever is in this integrand is 0. So if you make that equal to 0, this is the equation we get. Again, all these tenses, this q double prime, tau bar, and these terms are basically something that we do not, are not related with flow property. So we'll try to reduce it further. That's when we use the conservation of energy. So we know the work energy theorem, which you might have been familiar with before, where you know the net work done on an object is equal to the change in its kinetic energy. So from that we know from Navier-Stokes equations, we know that the net force is given by rho times dv dt. So this is basically this particular term is dv dt, material derivative of velocity, is whatever body forces plus whatever the surface forces that are acting. So if you multiply this force with velocity, we will get the kinetic, we'll get the rate of work done, and that should be equal to the change in kinetic energy. So if this is my kinetic energy term, so I just substitute the equation here, rho times, so this particular equation, I'm just substituting the kinetic energy term into this equation and saying that the rate of change of this particular quantity should be equal to the velocity times this particular force. If I just do a little rearrangement of these 2 terms, what I will be getting is this velocity term I'm clubbing together into this one, and I'm taking the internal energy terms together here, which will leave me that the net rate of change in the, this is basically rho times di dt, the material derivative of the internal energy equals to q triple prime is the rate of internal heat generation. This is whatever is the net heat flux leaving from the surface, plus we have an additional term here, which we want to simplify further. So yeah, have something. Okay. So this particular quantity is, if you write in an index notation, it will follow this particular, you can write this as tau ij times del ui del xa. You're already familiar with how to expand this term. So you have, this will turn into several expansions. So it will be like tau 1 del u1 by del x1. Just have to do this expansion. Plus so on. It's like you'll be having 9 terms like that. and that summation is this particular quantity. Because this energy equation is a scalar equation, this entire thing will evaluate to this thing. So if you keep writing the equations like expression like this, so then u1 by del x3 plus the other terms. I hope that is clear. So you have 9 terms here. Once you sum all of them, that is something we call viscosity. So what this equation tells us is the rate of change in with respect to the thermal energy or internal energy is because of heat addition, whatever is in the volumetric generation, whatever is leaving from the surfaces, and then we have something here which we are calling viscosity. We will see this later once we get the full derivation. So now again, this particular tau, whatever we are having, is not related to fluid properties directly. That's where the next thing comes, which is called a constitutive equation, where under again we are using specific assumptions like Newtonian, where the stress is proportional to strain, and then we are saying it is a Stokesian fluid, where we say that this particular properties, whatever you are considering, are independent of the direction in which you go. So there might be some fluids where if you apply stress in one particular direction, they behave differently, and if you apply stress in a different direction, they behave differently. Like those are anisotropic, but in this particular case, we are assuming that these properties are directionally independent. So that is a Stokesian fluid. Under those, yeah, yeah. Application as in, okay. So if you are familiar with this experiment where you have two plates, let's simplify this further. Let's say you have two plates, very thin film kind of stuff. One of the plate is moving upwards, and then you have some fluid between them. So basically, it's like you have a table, and on surface of it, let's say honey or something is there, and there is another plate on the top, and you're trying to pull this towards right. And we are interested in finding what is the force acting on the surface. But the things that I can measure here are only the velocity. Let's say I do not measure I can measure the force in a different way. If I can get the force directly, I can put some sensor here and get the stress also, stress directly. Instead of force, I can get, if I put a strain sensor or something here, I can get the stress directly. The question now is, how is the stress and strain related? In solids, we know that tau is proportional to that particular strain, and we have some constant g or y, or depending on whatever it is, depending on the type of load, we have to relate this particular strain with stress. Once we relate it, we'll be able to measure this and measure one of them, and we'll be able to get the other quantity, right? So in a similar way, for a fluid, all we are able to measure is velocity, and we are trying to get the stresses from the velocity itself. And in order to do that, we'll not be able to do unless we know the relation between stress and strain rate. Like in solids, we call strain. In fluids, it will be strain rate of strain rate. So what we are doing with this constitutive equation is we are reducing, like instead of measuring two quantities, we are doing it in a different way. We'll measure only the strain rate. Basically, we'll measure only the velocity, and then the fluid property in some way, where this fluid property will help you to find, like since we are fixing the relation like tau equal to mu times du dy or something, you'll only measure this particular you know why, velocity profile. From that you can calculate the derivative and fluid property in a different way, so that you will directly you'll be able to calculate tau in a scenario where you cannot where you do not have access to measure that directly. That is from if you want to see it from a mathematical point of view, we want to close these equations. So if you see our momentum equation or the continuity equation is expressed only in terms of velocity. But if now I have an equation like this, where I have tau or something which is not related to velocity, then I'll not be able to solve it. I need one more equation relating this tau with u. So it's basically, if I have my continuity equation which says ux plus vy equal to 0 in 2D form. So basically you have only two variables. And now I'm introducing another equation where I have tau. So this is an additional variable I'm introducing without an additional equation, which means now in this particular equation, if you see, I'm introducing internal energy and tau. Two terms I'm introducing. So I will not be able to solve this unless I have one more equation for tau. And that is where the constitutive equation comes. This is to say it in a mathematical way. In order to close and solve these equations, you need a different relation. And that has to come from experiments. or some fluid, that is where this fluid properties come into picture. So this is a way of relating your mathematical thing with the real world. So there should be some connection between these two, and that's where these things come. And these are all empirically determined ones. I mean, you cannot come up with a theoretical way to find these values of mu and lambda. This is where the real world connects with the mathematics or whatever simulations you are doing. Does that answer your question, or is there any query? Okay. Yeah, if you were to expand this particular terms again, like previously what we have is this term tau ij times del u by del xa. So a little bit of if you just multiply this with del ui by del xa, and then we take terms together, like we group terms like this and then simplify it further, the equation we'll be getting eventually consists of two terms. One is minus p times, this is basically divergence of u. So this will be something like the pdv work followed by another big term, which is the viscous dissipation that I was talking before. So this is happening because when the fluid is flowing, there will be internal velocity. Whenever there are internal velocity gradients, there will be a stress induced there. And because of that stress, if the velocities are very high, the gradients are too high, then a part of the energy will be, so a part of this kinetic energy will be converted into heat. So that is this particular term viscous, that is basically the viscous heating. So it's like when a fluid is passing through some high speed through a duct or something, then then heat will be internally generated. So this will be the internal generation, and this generation is purely because of viscosity of that particular fluid, because of the viscous nature of the particular flow. And this particular term is what we are calling with phi, denoting with phi. We can substitute both the terms into the previous energy equation. But as I said again, we have this I here, which is something that we do not measure directly. So we try to convert it into something that we measure. So that's where we have the enthalpy from thermodynamics. We can use the relation. Again, under specific assumptions, we can reduce this in a simplified form. So for example, if we have, let's say we'll start with a simple one. So if, yeah, you can see the derivation here. So I can substitute instead of I can substitute in terms of h. So that will give me rho is rho h minus p. And if you expand the terms, you'll have two terms, one with respect to the enthalpy and one with respect to the pressure terms. And from the enthalpy, again, we can convert it into, expand it into two terms. One concerning, like you can take the density out, then you have an enthalpy term, and you can take the density in, then you'll have the continuity equation coming back, so which is equal to zero because of the continuity equation gets satisfied. And then you have some pressure terms. So if we condense them together, so we have an enthalpy term followed by two pressure terms. And if you substitute them back into our original equation, so this is the final equation we have here. But then the problem now is, again, we have Qj, which is something that we do not measure directly. So we need to relate it in terms of things that we measure. So that's where we use the Fourier laws of conduction, where the Qj is given by minus k times. Again, this is for isotropic conduction, where you do not have any directional dependence. And then you take the derivative, the overall equation comes up like this. This particular term here, these two terms here are basically negligible when you have low speed flows or low Mach numbers. Whenever the Mach number is high, that's when these two terms get significantly higher. Usually these two terms will be sufficient. Now the question here is, I'm saying that Qj double prime is minus k times del t by del xa, and this particular thing is only for conduction. So I have derived my energy equation in this particular way. So does it mean, can I use it in case of convection, or is it restricted only for conduction? So whatever equation that we have derived here is not applicable for convection. You're saying so what do I do to make it? Say for example, I have a convection scenario. So what do I have to do here in case of convection? We are trying to come up with a differential form. So in this, if you are assuming convection, then what do we do to make it solve, or like how can we make it useful for convection? And why do you think it is only for like this won't apply for convection? if you recall the way we derived this equation, we assumed a small control volume, I mean a small volume dV, and this q double prime, whatever I am saying, is at the surface of the small volume dV. So in the integral form, it will be the entire surface. But when I write it in a differential form, it should be for the small volume, whatever is happening at the boundaries. So for this small volume, whatever is the way it is interacting with the surrounding fluid is basically because of conduction. Between this and then there is a neighboring volume. So at this point, at the point of contact, it's always conduction. Whenever we have two things in contact, it's always conduction. Even when you have a wall and some fluid is flowing on the top of this wall, at this point or whichever point I consider, between that point and the neighboring point, it will always be conduction. Is that right? Yeah. So to be able to use this for convection, all we have to do is consider multiple volumes like that. And then when you try to relate this with this, then the conduction is not applicable. So you have to solve all the equations together. Like you have to write this in differential form and then, I mean, in a integral form for each of these control volumes, and then solve them simultaneously together. So this and this are related to conduction. But if the energy is transferred from here to here, then that is by convection. So the cumulative effect of conduction of all this, and this will also be surrounded by other control volumes. So the net effect at this particular point, because of all these things, will be the convection point. But otherwise, between 2 points near the boundary, it is always conduction. Okay. Yeah. Now coming back, the equation previously, now we have written in terms of using Fourier's law of conduction, we can write it as internal generation plus k times delta T LXA. Plus these two terms are usually neglected for, let's say in case of liquids or even in case of gases where the velocities are very less, these two terms can be neglected. So I'll be focusing only on these two terms here. The term on the RHS is again Q triple prime is if you have some chemical reaction or some internal heat generation absorption, and all those things will be here. And T is something that we can measure. But on the LHS, we have enthalpy, which can be reduced further under specific cases. For liquids, you can write it as CPT. And in case of gases also, when under negligible velocities, you can write H as CP times T, where CP is the specific heat at constant pressure. There is a detailed derivation in the lecture video, which I would prefer if you can go through that. This is just to kind of make you understand intuitively. So H is basically CP times T. You can substitute that directly in this equation. It will give me rho Cp dt by dt is Q triple prime plus the conduction term. These two terms are usually neglected. This is with respect to the energy equation. Then comes the boundary layer flow. So the idea here is whenever you have a surface and some fluid is flowing over the top of the surface, like or when in contact with the surface, there will be two different distinct regions. The one very close to the surface, which is where the viscous forces are dominant. Again, in a fluid, the viscous forces are because of the gradients in the velocity. So near the wall, the velocity has to be 0. But then I'm saying there is a higher velocity on the top. So somewhere in between, the velocity has to change from 0 to this particular thing. So there will be some steep change in the value and then followed by gradual, eventually it will become uniformity. Wherever this steep change is there, that is what we are calling the boundary layer region. And then in the other region where this velocity gradients are negligible, we'll be calling that as an inviscid region. So this is like the classic equations where we have the continuity equation, x momentum, y momentum, and then we have the energy equation that we derived just now. So here in this boundary layer, when the velocities are very less, the viscous effects are negligible. So we don't have the mu phi term. And there are no chemical reactions or anything, radiation or anything of that sort in here. So the Q triple prime, the heat generation is also 0. So we just have the conduction term and then we have the advection term. Now we are making further assumptions saying that we'll reach a steady state. So there is no transient term in any of these equations. Again, all these are 2D equations. So whenever I say 2D, it is only true when we have the third dimension is basically very large compared to the other dimensions of in this particular scale. So when the plate is the width of the plate is very large compared to the other dimensions, then you can consider that particular flow to be 2D. And then we are also assuming constant properties so that this rho, mu, and all these things are constant. no dissipation I've already mentioned, and we are neglecting the gravity effect. Doesn't mean the gravity has to be zero. Basically, it could be like you have a horizontal plate where the gravity might not be affected, or the role of gravity is negligible compared to the other terms here. The velocity gradients are too high that the gravity term can actually be neglected. It's not like this particular thing has to be done in outer space where g is zero or something like that. All whenever we say no gravity, no dissipation, all that it means is the terms associated with that in the governing equation are small compared to the other terms. That's what we mean by whenever we say no or anything like that. Now to derive the governing equations, so these equations directly cannot be solved analytically, or even like unless you do some CFT or something, you'll not be able to solve this directly. So we have to reduce this in some form. So what people have come up with, like Laplacius Prandtl has come up with, is he observed from his experiments that there are two distinct regions, that inviscid and boundary layer, and then he applied something called scale analysis, which keeps coming up again and again, where the scale analysis is basically understanding what is the relative importance of these terms in the governing equation. So we have, for example, we have in the continuity equation, if we take the continuity equation, the velocity del u by del x, where x along this direction will be in terms of length. So x is varying from 0 to L or something. So L will be the scale for the x, and u will be in the scale of u infinity. But we want this entire term to be 0, which means the order of this and this should be 0. So for example, if del u del x is like say 0.1 meter per second, 0.1 per second, so it's basically meter per second by meter. So if it is 0.1, then del v by del y will also be in the same order. Only then this particular quantity will be 0. So if you apply that logic, del u del x will be in the order of u infinity by L, and del v del y will be in the order of v by delta, where delta is basically this length. And both of these orders should be equal, which gives us the velocity v should be on order of delta by L times u infinity. And from his experimental observations, he found that the layer of this delta by L is very less than 1. So since it's very small, velocity v is also negligible. So all that we have to care is the horizontal velocity here instead of the vertical velocity in the governing equations. So with that assumption, he neglected the d square u by del square u by del x square term. And then since v is very small, we can completely neglect this y momentum equation. So all he observed is we don't even have to solve this equation, because this, when you compare the order of the x momentum equation, this is in terms of u versus in terms of v, this v is very small, so you do not have to solve this equation, solve these terms or these terms. So which leaves us with del p del y equal to 0. When we say del p del y is 0, it means the pressure here and here will be same. Along vertical direction, if I draw a vertical line at any x, the pressure will be same vertically, but the horizontal pressure still remains. So for a flat plate, as I said before, outside we have an inviscid fluid. So inside an inviscid fluid, Bernoulli equation still applies. So from the Bernoulli equation, if the velocity is constant, then the pressure should also remain constant. Or if the velocity is changing, then you have to put that particular change in velocity, like use the Bernoulli's equation and then calculate the pressure from there directly. But for a flat plate, when free stream velocity is constant, then the pressure is basically constant. Like we have p infinity plus half rho infinity is equal to constant, and I'm saying u infinity is constant, which means this is constant. So dp infinity by dx is also 0 for a flat plate. So in case of a hydrodynamic boundary layer, the most important thing is, as I said before, is what is the friction here. So previously, before the boundary layer theory was there, the basic theory that is used is the potential flow theory, where we assume the fluid viscosity is negligible, and we were able to solve a lot of different problems. But then the main question that remained is, there is always friction that is acting because of the surface. So somewhere the energy is getting lost. And to account for that, we know there is a wall shear stress, but if you have a potential flow theory where you do not have these velocity gradients, then it basically tells me that tau w equal to 0, which is not true practically. So that's where when we use the boundary layer theory, this is again from the scaling analysis, we know u scales as u infinity and this scales as delta. From the previous relation, you can write it in this particular form, and this particular quantity is what we define as your Rex is basically this delta by L will scale as REL to the power minus half. So from there we can use that relation to get a form of this particular kind, and we define something called friction coefficient. Again, why do we need these things is because we can relate it with for a different velocity. Once I have CF, I do not need to know I'll solve the problem for one particular case and I can use it for a different case with a different U infinity value. So if the U infinity changes, then for that, if I know the CF, which is kind of a universal constant for this particular kind of flows, then like all I have to do is multiply that with U infinity square times 0 and I'll get the tau W from that directly. But all for that, we need to relate it in some way, which I can use it always. So if we substitute this equation back here, we'll have CF as a function of Rex to the power minus 2, but still we do not know the constant here. So until I know the constant here, I'll not be able to directly, like for a given flow, you will be knowing the Reynolds number from which you will be able to calculate CF. You know the free stream velocity from which you will calculate tau W. From which you can, once you know tau W, basically you know the shear stress. So from which you can calculate the net drag force or whatever is your, usually the interest will be the net drag force that is acting on the particular surface, which can be calculated from this tau W. All you have to do is integrate over the corresponding area and you'll get the force. In the next week lectures, we will see a way to solve this equation. Like now the idea is to only get the equation. So these are the governing equations. And this particular term will be 0 for a flat plate. Yeah. Okay. Okay, sure. So have you gone through the lecture video? So I am under the assumption that you have already gone through the lecture videos and this is kind of a summary. So, okay. Okay, okay, okay. Okay, I understand. So, okay, I was under the impression that you have already gone through the lecture video. So this is kind of a summary. If you have not gone through, so where were you lost? So up until where were you clear? Was it from the beginning or somewhere in between? Yeah, okay. That is the last part. So that is, so this is basically, so till here you must be clear then. So this is basically the boundary layer equation. This is lecture 4. So, okay, so energy equation you are clear, right? Okay, so in the boundary layer flow, uh, okay, forget about the lecture videos for now. So in whatever we are discussing now, till where were you, like where were you lost? Where did you get lost? Is it in the beginning of the boundary layer or is it somewhere along the line? So maybe my pace is too high. I'll speak little slowly. So these equations are clear. This one before, okay. Till here, okay, okay. Let me go a little slow. So just let me know if there is some problem. I'm also kind of doing it for the first time. So okay, I'll speak a little slower. So still this equation you are clear. Yeah. Till this equation it is clear. The only problem with this equation is the enthalpy H that we have here is something that we do not measure directly. So I want to write it in terms of temperature. So one equation that we already know is H is Cp times T, like under isobaric conditions, where Cp is basically the specific heat at constant pressure. So all I have to do is substitute this into this equation. So that is what I have done here. So this term here can be written as dHdT, which is the material derivative. So if I substitute H equal to Cpt and take the Cp out like for a constant property, so it will be rho Cp dt by dt. So that is what I have written here. So rho Cp dt by dt is whatever is on the RHS. So again, this is assuming that the pressure changes are negligible. When you have a liquid where the pressure changes are very negligible, this dp dt can also be neglected. So this will be my energy equation. Now, when we have gases where P may not be constant, which means this dp dt term may not be zero, then you will have that additional term here. But usually for low speed flows, even though gases are highly compressible, but when the speeds are low, when the Mach number is very low, Mach number is basically the velocity with respect to the speed of sound in that particular medium. If this Mach number is less than say 0.1, then both the terms are actually very small and they can be neglected from the total governing equation. So this will be the only term that I will be considering for most of the cases from now on. Even in the boundary layer equation, this is the equation that we'll be using. If you see the boundary layer equation, it will be rho Cp this equal to some thermal conductivity times the temperature gradient, like the Laplacian term. We don't, again, here we do not have any heating effects, so Q triple prime is not there. And because the speeds are very low, like the Mach numbers are very low, we do not have the dp dt and the mu phi terms here. That's the gist of this. Now coming to the boundary layer flow. Okay, I hope this is clear up until now. Now for the boundary layer flow, what we have is we have some surface, some object and some fluid is flowing on top of that particular surface. Just to know, you have done any fluid course before, some incompressible flow or anything before? Have you done any fluid course, incompressible flow or any other fluid mechanics course? Okay, you have not done a fluid mechanics. So you are comfortable with these equations, like the x momentum, the Navier-Stokes equations? Okay. So let's say you have some surface like an aeroplane wing or let's say a flat surface, and then fluid is flowing on top of that flat surface. So you have a road, something like a road like this, and then you have some wind flowing over the road. So what we are trying to find now is what is the velocity field that will happen on the surface of the road. That is what we are trying to find here. And to do that, we have to make certain assumptions. In reality, it will always be some 3D thing, but we are assuming that it to be a 2D, which is a reasonable assumption when the width of this particular is very small compared to whatever we are our region of interest here is. So when you have the width is very large compared to this particular length, then we can make this assumption of 2D steady state, so that our whatever the time derivative terms that will come here are neglected. And then we have a laminar flow, which is basically means that the fluid is flowing in terms of layers like this. We'll discuss that more, like it become more clear once the turbulence comes into picture. And then we assume constant properties like the rho and the mu that we are considering here are not changing with respect to time or any other things. And then we say no dissipation and no gravity, which only means that the terms are neglected in the governing equations. So, gravity can be neglected not because gravity is absent, but because the velocity gradients are too high that these terms will be say in the order of 100 or something. The gravity term will be, let's say 100, 10, then it will be 1000 or something. So compared to this, when you add 10 to this, it will be just 1010, which can actually be neglected. So when we say no dissipation, no gravity, it only means that the terms when you add, the effect on the overall velocity field or something are negligible. But the equations, even these four equations that are given here, so you basically have four unknowns here. So we have u, v, p and t. I have four unknowns and I have four equations. So I should be able to solve them provided I know the boundary conditions. If I know the boundary conditions, I should be able to solve them, but these equations are too difficult to solve directly. So then what people have done is Prandtl came up with a way to simplify these equations. So what he did is something called scaling analysis, where he tried to understand, okay, I have to neglect some terms in this, only then I'll be able to solve them. But to decide which terms to neglect, he came up with something called scaling, where he said that the velocity u this particular velocity u will be scaled with u infinity. So you will say u as order of u infinity, which means that if u infinity is 0.1 meter per second, this u will be somewhere in the same lines. So it will also around somewhere close to 0.1, and x will be in the order of L. With these orders, what he tried to understand is use this in each of these equations. So when he did that for continuity equation, we have two terms here, del u del x and del v del y. So for the sum of two terms to be 0, both of them should be of the same order. So if it is, say, this is 0.01, the other one should be minus 0.01. Only then this will be 0. If this is, say, 1 of order 0.01, like if the magnitude of this is, say, 0.01 and this is, say, 100 or something, then it will never be equal to 0. So for this to be 0, both of them should be on the more or less same order. So with that idea, what he did is, the first one will be in the order u infinity by L, and the second one will be of the order v he took as some v, and y, for x is scaling from 0 to L if the length of the plate is L, and along the y direction he took delta. Delta is the boundary layer thickness. When we say boundary layer thickness, it's basically the height at which the velocity will reach, say, 99% of the free stream velocity. If the velocity here is u infinite, then the velocity at this point is 99% of u infinity. So that particular distance is what he defined as delta. So we define the order of this quantity as v by delta. So both of them should be of the same order. So v should be delta times u infinity by L. And from his experiments, when he did experiments, he found that he measured velocity at different points, and from that he determined the values of delta, and then he found the delta. He calculated delta by L, and that value is very, very less than 1, very much less than 1. That's what he observed from experiments. So with that observation, he went back to the governing equation, and he applied that to this particular term, del square u by del x square and del square u by del y square. Like in my x momentum equation, I have both these terms. So if you observe that, if you apply that to this particular term, so what will this be? So it will be u infinity by L square, and this term will be u infinity square by delta square. He observed that delta is very, very less than L, so which means u infinity by delta square should be very much higher compared to u infinity by L square. So what he did then is, okay, in this equation I do not have to consider this term, I can neglect this term. That's the conclusion he came to. And in a similar way, he applied that he know that from the continuity equation we know that v is delta by L times u infinity, and this itself is a very small number. So v itself is a very small number, which means in this y momentum equation we have del v del x, del v del y. All these terms have v in it, and all of them can be neglected. So when all of them are neglected, what this will end up giving me is del p del y equal to 0. When we say del p del y equal to 0, what we are saying is, if I draw a vertical line at any point along y, the pressure will be constant. That's what we'll be getting from here. So if del p del y is 0, this means p is only a function of x, which means this term still remains. Then he applied another thing. From his observation, he found that there are two distinct regions. One region where the viscous stresses are very large, and another region where viscous stresses are not there at all. When there are no viscous effects, then we can apply the Bernoulli equation. So from Bernoulli equation, he said that p plus half rho u square equal to constant, which we already know before even the boundary layer theory came. So in case of flat plate, when you have a constant velocity outstream, this is what we call a free stream velocity, and when this is but constant, this rho u infinity square is constant, which means p infinity should also be constant. So if p is constant, then dp dx should be 0, which means this term is also neglected. This is true only for a flat plate. And when you have the free stream velocity, constant free stream velocity, then this term is also neglected. So all we'll be left with is rho u del x plus v del u del y equal to mu times del square u del y square. And this is my continuity equation. This remains the same. So from these three equations, now we reduced it to two equations. And even within the two equations, now it reduced further, like we removed this term and this term. So this is a these equations are simplified from the original equation, but still we do not have a way to solve them. How to solve them is something that we will see in the next week. But even without solving this equation, we can make some insights from the equation. So we know that this delta by L, So we want to understand what is the scale of this delta by L. So if you see this equation, so if I apply the scaling analysis here, so this will be this first term. So it will be rho times u will be scaled as u infinity, and this will be scaled as u infinity by L. And even if the same goes here for mu times this one, which will be mu times del square u by del y square. So this will be something like this. So I'm saying that this is again, since we neglected only this term and still these two terms are remaining, which means both of them should be of the same order. So from that, what he deduced is if both of them should be of the same order, we just rearrange this equation. So this will give me delta square by L square should be of the order mu by u infinity get cancelled, and you have rho u infinity. Since I put L square here, which means I have to multiply with another. And this particular quantity is what we call the Reynolds number, where REL is rho u infinity L by mu. So from there, he deduced that delta by L should scale in the order of REL to the power minus half. So what he found from experiments is this particular quantity is very much less than 1, which if you just if this is very much less than 1, then the inverse of this should be very much greater than 1. So if the Reynolds number is very much greater than 1, then in that particular case, you can this particular whatever we are doing here is valid. That's his final conclusion. So again, when you have a long plate near the initial region, in this region, the length, if you consider only in this region, the length will be very small, and this particular assumption might not be valid. Only if you are sufficiently far from the origin, that's why the origin is not, it's chosen slightly far from this particular point. So only when you are sufficiently far downstream from the leading edge is where this comes. But that's when these particular assumptions are valid, and these equations you can solve. Right? When you solve these equations, the solution you're going to get is going to match with whatever is happening in the reality. Without even solving, this is the conclusion he came to. Now, the interesting, the main object of doing all this analysis is to understand what is the net force acting on the plate. So you have some plate or some surface, and then some fluid is flowing on the top of the surface. Now, as the fluid flows on the surface, then it will try to drag the surface along with it. So which means there will be some force acting on the surface by the fluid, and we are interested in that force. Otherwise, we will not be able to design the surface correctly. If you design a surface that cannot withstand that particular force, then the surface will just peel off from whatever it is holding on into the base. So we need to calculate the total force, and for that we need to be able to calculate what is the stress acting on this. From Newton's, for a Newtonian fluid, we know that wall shear stress, or basically the shear stress, is mu times del u del y. This is again where the constitutive relation is used. Yeah. You're saying something? Newtonian fluid is one where the stress is proportional to the strain rate. Like this proportionality is a constant, then you call it a Newtonian fluid. If it is a non-Newtonian, then you'll have something like this, where you have some power. It won't be linear thing. It will have power 0.1 point, different values. Depending on the exponent, you have different kinds of fluid. Air is basically a Newtonian fluid, so we can still use this thing. Like his experiments were on air and water, which are Newtonian fluids. Now, using the scaling analysis, we know that u will scale as u infinity and y will scale as delta. So tau w should scale as mu times u infinity by delta. We'll just rearrange this equation, just multiply and divide with x. So we'll have x by delta. We know previously that delta by x will scale as rex to the power minus half. So x by delta should scale as rex to the power half. So we know tau w will scale as this. But the way in which this is defined, tau w is something, if u infinity changes, then tau w will keep on changing. So we want to come up in a way that we can use it for different cases independent of u infinity. So then we have to define some other way. So just like Reynolds number, he came up with something called friction coefficient, which is defined as the ratio of tau w to half rho infinity scale. It's just non-dimensionalizing the wall shear stress. Again, if you apply the scaling analysis, so we know tau w will scale as this, and once you divide it with rho infinity square, and you just rearrange this equation, so u infinity gets cancelled. You have mu by rho infinity x. So this is basically my 1 by Reynolds number. So this will be rex to the power minus half. So the skin friction coefficient will scale as rex to the power minus half, which is same as delta by x. Even delta by x will scale as delta by L will scale as REL. If you replace this L with x, it will be rex to the power minus half. which means both the screen friction coefficient will also scale as delta by x. So for a given length of the plate, if you have a thicker boundary layer, which means you have a higher delta, then CF will also increase. So which means for the same free stream velocity, you will have more shear stress. So the drag force will keep on increasing, or the viscous effect will be higher when you have thicker boundary layers. Now this is all with something called hydrodynamic. We only discussed about velocity here, so this is a hydrodynamic boundary layer. The next thing is for a temperature. Whenever you have a temperature, then you have some thermal boundary layer, which is also very similar. So very close to the wall, you will have high temperatures, and far from it, the temperatures will eventually reach the free stream temperature. And the thickness where it reaches 99% of the free stream is, we define it with delta T. Just like delta, we call it delta T, which is the thermal boundary layer thickness. So the previous boundary layer equations are still valid. Now we have to reduce the energy equation. So following the same logic as before, along x, L is much higher compared to delta T. So the gradient with respect to s will be will be very less compared to y. So the energy equation will reduce to this particular way, where alpha is just divided with rho Cp. So it will be k by rho Cp. This is called thermal diffusivity. So now I have three equations. So one continuity equation, and for a flat plate, this will be 0. And then one energy equation, and I have three unknowns. I need to find u, v, and t. Three unknowns and three equations. If I know the boundary conditions, I should be able to solve it. Again, this will also be in next week. Again, without even solving this, just to make a little insights from the equation, again we do the scaling analysis. Now we have to choose a scale for y, which we do not know as of now. So we have two possible conditions. One, we have delta t, and another we have delta. Now we can have like either both of them to be equal, or one of them to be, like in this picture, delta is greater than delta t. So what is the physical significance of that, and what happens if delta t is greater than delta, are the two scenarios that we'll be considering for that. So now let's say if delta T is greater than delta, so thermal boundary layer thickness is higher than the hydrodynamic boundary layer thickness. So from the energy equation, we know that the advection term, this is U times del T del X, and the diffusion term, both are the same order. Otherwise, that equation will not exist. So this T will have some scale delta T, and X will have L. U will have U infinity. Should scale as alpha times T, again delta T, and Y will be delta T square. So from this, if you rearrange just like before, we'll have delta T by L square should be proportional to this particular quantity. Again, this is basically my Reynolds number, and this is something called Prandtl number. PR is the Prandtl number. So delta T by L should scale as REL times the Prandtl number. So previously we just have the Reynolds number. Now we just multiplied with something called Prandtl number. And if you divide it to understand what is the ratio of delta T by delta. So we know delta by L will scale as 1 by square root of REL. So if I divide this with this, I'll be left with 1 by Prandtl to the power half. So if the Prandtl number is less than 1, then delta T will be greater than delta. So for a fluid, you'll always be given the Prandtl number. So for air, Prandtl number is like 0.71 or something under ordinary conditions. So that is close to 1. So both the thermal and the hydrodynamic boundary layer thickness are almost same. For when you have liquid metals, the Prandtl number will be like say 0.01 or something, which will be very much less than 1. Then you'll have the thermal boundary layer thickness very much higher than the hydrodynamic boundary layers. For some gases and some oils, Prandtl number will be greater than 1. That is the next case we will consider. So you can just say from this equation, if Prandtl number is greater than 1, then it will be reversed. So the thermal boundary layer thickness will be less than the hydrodynamic boundary layer thickness. But the interesting thing here is, okay, we identify that from the Prandtl number, we'll be able to say which of them is higher or not. And why do we need that? Is because we need to choose the appropriate scaling. We are choosing delta T as my scaling. If I choose delta T as my scaling, then the velocity, I can take the velocity scale as U infinity. If the flow is reversed, if this is delta and this is delta T, then I will not be able to take U infinity directly. Because if you have a different flow where you have this as delta and this as delta T, then I cannot take this as my scale, because you see the velocity, like most of the reason the velocities are different from the velocity here. Like then what to do is something that we'll see a little later. But now for this particular case, You can, yeah, yeah. I didn't get which particular point. Here, this is the velocity profile. This, okay. No, here is where you have the highest velocity. The inviscid region is where you have the highest velocity, and this is the next highest, and this is the least. Like you can see the arrow size. The arrow size is basically signifies the magnitude of velocity. So close to the wall, the velocity has to be 0. As you go away from the wall, the velocity keeps increasing. Yeah. Now the next thing is the heat transfer coefficient. So the way we define heat transfer coefficient is the heat flux divided by the temperature difference. And we know the heat flux is, again, as I said before, it will always be conduction. If you consider at any point, it will always be through conduction. So at the contact surface between the solid and the fluid, it will be because of conduction. So all I have to do is minus k times del T del y at that particular surface where y equal to 0. And this k is that of the fluid. If you apply the same scales, T will scale as delta T, y will scale as, sorry, let's say this is T and this is delta T. Tw minus T infinity is again delta T. So H will scale as k by delta T. And if you define the Nusselt number previously as hx by k, so that all I have to do is bring this k here, multiply with x, so that will be x by delta t, which we know from previous that x by delta t will scale as the inverse of this, so that is Rex to the power half times Prandtl number. So if I calculate the local Nusselt number, that should be in this relation, like it should be proportional to this. We still don't know what the constant is. If you know the constant, then the problem is solved. That again will be discussed in the next week. But even without solving the equation, he was able to use the scaling analysis to come up with this relation that if you get the experimental data, the kind of fit you are going to make is dependent on this relation. Now coming to the next case where you have delta T to be less than delta, where the hydrodynamic boundary layer is much larger compared to the thermal boundary layer thickness. I think, sorry, I think I have drawn it wrong. So this scenario is basically delta greater than delta T. So here what happens is within the thermal boundary layer, the velocity has not reached u infinity yet. So it will be less than u infinity. So I have to accordingly change the value of reference velocity. So what we do is use the similarity principle, uh, which again we'll discuss in the next week. It will be clearer in the next week. But for now, you can just assume that you can take it as u with, if these are my boundary layers. If the velocity here is u and the velocity here is u infinity, and let's say it is, you can apply the similarity principle, which says that u infinity divided by this whatever total delta and the u here divided by delta t are same. So all we are saying, it's like apply the similarity triangles. So you have u here, so u by delta t should be on the same order as u infinity by delta, from which we will get u to be of the order of u infinity times delta t by delta, which will give you this equation. Now, from the continuity, from the previous relation, continuity equation, we can say del v del y and del u del x should be of the same order. So if you substitute that back here, you will know that v should be on the order of this. Once we know the order of u and v, again we'll do the same analysis as before. Again, we will take the energy equation. We will see what is the order of terms of the advection and the diffusion terms. So you substitute order of u as this quantity times del t del x is delta t by L should be on the same order as this. So from this, all we are trying to find is what is the order of delta t by L, so which is this particular equation. So if you just rearrange the terms, you will get delta t by L should be of order of, this is basically 1 by Prandtl number, and this we know previously that it should be 1 by RL to the power half, and this quantity itself is my Reynolds number. So delta t by L should be should be of the order Prandtl to the power minus 1 by 3 and Reynolds to the power minus 1 by half. So again, if you do the heat transfer coefficient, which we already got before, H should be of the order k by delta t, and NUX we just got previously. NUX should be x by delta t, so which is inverse of this. So NUX should be Prandtl to the power 1 by 3 and Reynolds to the power half. So when we have, so if delta t is less than delta, then Prandtl number is greater than 1. So for fluids with Prandtl number greater than 1, the Nusselt number follows Prandtl to the power 1 by 3 times REL to the power half. And for fluids with Prandtl number less than 1, which is the previous case, we'll have Rex to the power half and PR to the power half. The exact constant coefficients that will come here is something again. Once you solve the equations, you'll get these constants. Once you know the constant, all we have to do is get the Nusselt number. From the Nusselt number, calculate the H. You know the temperature of the surface and the free stream, so multiply that the temperature difference with this H, from which you can calculate the heat transfer. Yeah, that is with respect to the concepts of this particular week. Now I'll have some problems here. So I would like you to solve these problems. So consider a flow accelerating through a duct of variable cross section. Let's say you have something like this. If the largest velocity gradient measured locally is du dx, so you have some fluid flowing through it. And I'm saying that du dx is the largest, which means along the y direction the velocity gradient is negligible. So it will be more or less uniform. The fluid is going out. And the largest density gradient is also along the x direction. So which means along y, so it's basically 1D flow. What should be the order of magnitude relationship between du dx and d rho dx for the incompressibility assumption to be valid? So I want to know whether I can use the incompressible flow equations that we have derived in this particular course. In order for this relation to be valid, what should be the order of magnitude relation between du dx and d rho dx? Yes, that's why we have du dx. So if this is x direction, your velocity keeps changing along the x direction. So how do you approach this problem? So what is the governing equation that we'll use here? Assume that this is steady flow. That will kind of simplify the things. No, I want to understand the relation between du dx and d rho dx. Like gradient of density and gradient of velocity. I want to know the relationship between those two quantities. Okay, even before that, what is incompressibility assumption? If I write my continuity equation, it will be something like this, right? Del rho del t, or if I write it in the material derivative form, it will be, or I will write it in some plus. If the other gradient is, this is basically my continuity equation, right? And I'm saying it is a steady flow, so this is 0. So all I'll be having is u times del rho del x plus rho times del u del x equal to 0. Now, what is the condition for incompressibility? Okay, how to approach it? Yeah, so when we say an incompressibility, like in all the previous equations, if you recollect, so when we are saying this equation, this we are saying is a continuity equation, right? Del u del x plus del v del y equal to 0. This equation is valid only when it is an incompressible flow. So the assumption that is not stated here is that this is an incompressible flow. So we're assuming that del u del x plus del v del y equal to 0. That is kind of an implicit assumption that we have here. So in this particular case, I'm saying that only one gradient is there and the other gradient is 0, which means I'm saying that del u del x is almost from the order of 0, which I'm saying that del u del x is the only term that is existing. And for continuity equation to be valid, this should be like very less than 1, or you can say practically to be 0 or of that sort. So which means in this equation, if I just take the row out this side, so it will be plus del u del x equal to 0. And in order for this to be incompressible, I want this term to be very much less than this. Only then this equation can be converted into del u del x equal to 0. So the order of this equation, which is u by rho times del rho del x, should be very much less than the order of del u del x. Like the magnitude wise, if I calculate the magnitudes, then the magnitude of this particular quantity should be very much less than the magnitude of this. Only then I can neglect this equation, so make this close to 0, which means del u del x would be equal to 0. And this is what our continued incompressibility assumption is for a 1D case. Okay. Next problem is on something called a field. So the problem is like this. So you have some wall, which is at temperature T0, and then you have an extended surface from the wall, which is going to infinite. So you have a very thin surface, and that is extending to infinity. A is the area of this particular, I consider a cross section like this dotted line cross section. A is the surface area of this cross section area of this one. Q triple prime is the internal heat generation inside this entire quantity per unit volume. K is the thermal conductivity of this particular thing, and T of x is the temperature along the x direction. So I'm saying it is a one-dimensional flow. So temperature is only varying along the x direction. Like there is no variation along the other direction. There is only one temperature variation. And the governing equation is like this. So this is slightly different from the previous equation we have seen. For one fact that there is no velocity here, because we are writing the governing equation inside the solid medium, where the advection component velocities are very less. So there is no convection term. We still have the internal heat generation term, and then we have the surface term. So if you recollect, the energy equation has three terms. This is the heat generation term, this is the diffusion term, and then we have the net surface term. The surface term I'm writing as h times delta t times the net area, where this p is basically the surface area, this the perimeter. So per unit length, h times perimeter times T minus T naught, where T is the temperature at that particular surface. So whatever is because of conduction minus whatever is leaving because of convection plus the internal heat generation, the net heat energy should be balanced. So this is the governing equation. Is the governing equation clear? Yeah. Yes. Yes. Yeah. The numerical problems will start from next week, because you have not, since we have not solved the governing, like this week lectures is only on derivation, so I focused only on scaling analysis and derivation. Next week we will actually solve some problems. Like once you have those constants, you will be able to solve the problem. Now we only have the scaling analysis. Yes. Yes. Every week till then, till like around 12 or 12 weeks course, right? So we'll have 13 sessions. So the idea is even without actually solving the problem, you will be able to get some insights from the equation itself from scaling analysis. That is the whole point I would like to get from these problems. So if you see, we know we can write the governing equation. Now I can't solve the equation at this point, but I can answer some questions like, say for example, this particular one where it says that if x is large enough, when you are very far away from this, what should be the order of conduction term in the equation? So do I have to solve this entire equation? So if I'm saying x is very large, so what can I say about this in this equation? If x is very large, then what will be the order of t? T. What will be the order of temperature T, not heat? Okay, we'll see whether it is increased or decreased. But it's not about increase or decrease, but what will be the order in the sense? Let's say here I mentioned that T infinity is the temperature far from the wall. So as x tends to infinity, T will be in the order of T infinity, right? I mean, that's what I was intending. So it will be T infinity times some plus or minus something, but it will be close to T infinity as x tends to infinity. In that case, the conduction term will be basically Ka times T will be T infinity times the x square or something of this sort. So this will be the conduction term, and as x tends to infinity, this term goes to 0. So which means far enough from the plate, all you have to solve is this equation. So the conduction term is actually negligible when you go far enough from the plate. If for example, if you say T naught is higher than T infinity, then the temperature will keep on decreasing. If it is other way, then the temperature will keep on increasing, depending on the relative magnitudes of T naught and T infinity. But the idea is this term can be neglected. Now, if the term is neglected, what is the fin temperature? So if this first term is neglected, all we have is Hp times T infinity minus T naught plus Q triple prime A equal to 0, which will give me T infinity as T naught plus, I don't even have to solve the differential equation. If I know that x is very large, so this is kind of order of estimate, like the final temperature will be T naught plus this particular quantity, will be in this order. Now let us put in another way. Now let's say I want to find a delta where the heat transfer is ruled by balance between conduction and internal heat generation. So basically I want to know what is the region of from this point, how far can I go? Like as you are close to this temperature, T naught will be the temperature will be, if x tends to 0, then I can say that T will be close to T naught, right? If T is close to T naught, then basically T minus T naught is close to 0. So I can neglect this term. So what is the range from 0 to whatever that delta, where I can assume that this convection is neglected? So again, if you apply the same scaling analysis, so this will be Ka times T naught by delta square plus, sorry, this should be the same order as Q triple prime times A, which means delta should be of the order of square root of this particular quantity. So depending on which region you are interested in, so if you substitute the values of K, T naught and Q triple prime for your particular problem, and if you are located far away from the source, you can basically, if you are very close to the source, then you can neglect this particular term. If you are very far away from the source, you can neglect this particular term. If you are somewhere in between, that's when you have to consider all the terms, and then you have to solve the full equation. So even before trying to solve the problem, we are trying to kind of simplify it into our particular case. That is where all the scaling analysis is about, to get insights from the equation without actually solving the problem. This is a slightly different problem. How familiar are you with optimization? Minimizing something or maximizing something. So let's say I have a problem. In this problem is basically you have some furnace which is at a high temperature, and then there are some low temperature components. Still, all are higher than the ambient temperature. All we are trying to do is we have to put some insulation on the surfaces. I have a certain volume of insulation which is fixed. All I need to determine is how much thickness should I use for this furnace and how much for this other one. So I have a, yeah, so I want to do the split in such a way that I'll minimize the total heat loss. So here what we are trying to do is if you if you increase the insulation here, the thickness of insulation for this component, the thickness of here the thickness will reduce. If you do if you try to change this one, the other one will get affected by it. So one way or other, if you try to decrease QH, your QL will increase. If you try to decrease this one, the other one will increase. So you have to come up with a balance. That is where the optimization is about. Have you done something like that? So it's mathematically it is straightforward. No? Okay. So here it is straightforward. So all we are trying to do is minimize QH plus QL. So if I write Q as QH plus QL, uh, uh, I'm saying that it is only through conduction, like the heat loss is only because of conduction. So I can directly write it as K times area times delta T is TH minus TO, so whatever is the thickness, plus QL is this. So from whatever is inside to the particular insulation material, it can be because of anything. From the insulation to the ambient, it is because of convection. But but we are saying that it's a study. So you have something like this. Let's say this is a hot furnace, and then you have some insulation on top of it. So from the insulation to the ambient, it will be convection. From the internal thing to this could be something else. It could be because of radiation. So depending on whatever is inside this furnace, it can be because of radiation, convection, all combined also. But what we are interested in is if it is in steady state, then whatever heat that is coming from here should be leaving from outside, right? So in that case, all I have to do is if I know the temperature here, if I take and inside the insulator is a material where we do not have convection or radiation. So the only possible mode of heat transfer is conduction. So heat here equal to here should be equal to whatever is going inside, and whatever is going inside I can do with conduction. So if I know the thermal conductivity of the insulator times the area of that particular insulator times whatever is the temperature difference across the insulator divided by thickness should give me the heat transfer, right? Okay. And what we are trying to do is minimize this particular Q. And however we are trying to do this is we need to come up with the ratio TH by TL. So now the tricky part is we are saying that TH and TL are not independent. So if I want to kind of optimize this, if I want to minimize this Q, all I have to do is make TH equal to infinity and TL equal to infinity, right? If I just make both of them to be infinity, then Q will be 0. But physically, we cannot do that. So there are always some material constraints, cost constraints, whatever constraints are there. Here the constraint is we are saying the total volume is fixed, which means we have to minimize this Q subject to another condition, which is volume is constant, where volume is basically AH times TH plus AL times TL. So you have no volume of the total insulation that is available to you. So with this particular volume of insulation, you have to minimize your Q. So how do you distribute it between this surface and this surface? That is the question. Okay. So how do you solve this problem? Okay, since you are not familiar with optimization, so this is basically there is something called Lagrange method where you come up with a function called Lagrange, which is your object. Your objective is to minimize something. So you write the objective minus Lagrange multiplier times whatever your constraint is there. Constraint is this particular equation, which is B minus AHTH minus ALTL. And what we are trying to do is minimize this particular L with respect to the variables, whatever we have. So my objective variables are TH by TL, or let's just say TH and TL here. So I have to vary TH and TL in such a way that this entire quantity is minimized. So which means, from calculus, we know that if you want to minimize something, then all you have to do is, okay, I have three variables here. So I have to find TH, TL, and lambda. So I have three variables, so I need three equations. So the equations will be something like, if you want to minimize a function f with respect to x, all we have to do is del f by del x equal to 0. So similarly, you do del L by del TH equal to 0, you'll get one equation. Del L by del TL equal to 0, the other equation. And del L by del lambda equal to 0, which will basically give you this equation again. So you have three equations and three unknowns. So you should be able to solve and get the values of TH and TL. So for this, it is straightforward. So if I just write dl by dTH, so that will be minus k ah by th square, th minus to, and plus lambda times ah. And I'm saying this should be equal to 0, which will give me lambda equal to k by th times th minus to. If I do the same for the other one, other thickness, that will also give me another equation, which is lambda is k by, it's just that h will be replaced with n. Like, I don't think that is straightforward. Since both are equal to lambda, so both have to be equal to each other. So which will give me sorry, there is a square here I missed out. So from this you can directly get th by tn. Is clear? Okay. But now from a practical point of view, so okay, let's go to the next problem. So there is this, what we are saying here is all you have to do is minimize this QH plus QL. So the question now is, this is at a higher temperature, this is at a lower temperature. So do I have to give equal weightages to both of them? So for example, QH, let's say here 1 watt is lost. Here also 1 watt is lost. All we are, when we are doing this optimization, we have given equal weightage to this. So if I can reduce 1 watt here, I can also reduce 1 watt here by this particular whatever optimization we have done. So does it really, are these both the same? So 1 watt lost from this and 1 watt lost from this, are these both the same? Okay, on what basis were you saying that? Because it is at a higher temperature. Okay, so you're saying 1 watt loss from a hotter furnace because it is a higher temperature shouldn't matter much compared to a lower one. Okay, that could be okay. Let me put it in this way. So if you are saying something is lost, basically it means that you cannot use it for something else, right? That's what we are saying. We are saying this QH is lost because we are not able to use it for anything, right? So the question now is, how can I make it, put it to use? So if I were to use this energy, whatever is lost from here, if I want to use it for something, which of these 1 watts will be more useful for me? The one that is coming from hotter temperature or one that is coming from the lower temperature? Which will be more useful to me? Or both are the same? Yeah, the amount of energy that is lost is 1 watt. But let's say this is from 500 Celsius and this is from say 40 Celsius. So the energy that is available to me is same. So so unless I can't make use of it, it is still a loss. So which of these, like, does it mean like this loss and this loss are the same or they're different? Okay, so which of this can you put to use? You can put to use. So which means if I lose 1 watt here, I'm basically having an opportunity. If you're familiar with economics, and that you're losing more here, right? So 1 watt if I lose here, which means I have lost something much more than here, right? So instead of thinking in a way where you have since just because it has more doesn't mean it has to lose more, because it is at a higher temperature. If you lose even a less quantity in this, that could actually have been put to much better use compared to the one that you're losing here. So this should be better insulated than this, right? If you think in those terms. So if that is the case, then the way we have derived this optimal ratio, whatever it is here, is we are assuming that Q equal to QH plus QL, which means both are given equal priority. Like if I lose 1 watt here or here, it doesn't matter. That's how I've derived this entire thing here. Which means like the math is good, but then unless you know the real things, you cannot directly apply it to some practical purposes. So you have to know what you are solving for, like why you are solving. Only then all of this makes sense. So now the question is, how do I give the relative importance to both of this? That's the next part of the question. So what we try to do now is there is some heat rejection here. Now we will put a Carnot engine here. I think you are familiar with thermodynamics, right? Yeah. Now if I put a Carnot engine, I can get some work here. What we're trying to do now is, okay, instead of minimizing the total heat loss, we will try to minimize the lost work. This work is something that we are losing, that we are basically it's lost because we are not able to get it, because we are directly leaving the heat to the ambient. Ideally, we do not have a Carnot engine, so we are losing this amount of work. So what we try to do now is minimize the lost work. So instead of minimizing QH plus QL, we will now minimize WH plus WL, and then determine the what is the optimal thickness ratio. Can you do it? Just like the same as before, but instead of QH and QL, now I'm writing WH and WL. Yeah, yeah, it's an ideal case. Like this is the maximum possible work loss that you can get. In reality, you cannot achieve it, but again, that will kind of give you an estimate of how much weightage you have to give for this and this, right? Like we need some weightage for QH and QL. So this will basically become eta H times QH plus eta L times QL. So from previous, we know that I cannot directly write QH plus QL. I need to give some weightages for them. And we know eta H is higher than eta L. So this way, when you do the optimization, it will know that I have to give more importance to minimize QH than QL. Like we know the intuition, all we have to do is put it mathematically before solving. This is just one way to give the weightages. You can just put 2, 3 different numbers and do that, but this is a more systematic way to do it. Okay, now what is eta H and eta L? This is the Carnot efficiency. Still the volume has to remain the same. So same, just like the previous one, all you have to do is take del L by del TH equal to 0. Then you can solve and tell me what the answer you're getting. Is this the same you're getting? We'll do some calculations. The previous one was square root of th minus t naught by something. Now it is th minus t, it's this different one. Now the interesting question is, now we got two different answers. So one is this one, from the problem 7 we have this, and from problem 8 we have this. Which of these two is higher? Which one would you use? I think this is clear now, right? If you use the seventh problem one, then basically you are assuming that both are equal weightage, which is not practical. So it's better to use this one than this one. The question is, which of these is higher, 8 or 7? So you are saying 7 will be higher than 8. Okay, why? Like, you did something. Okay, if it is based on Carnot cycle, then why would it be higher? Yeah, no, this is the thickness ratio, right? Thickness of the insulation. This is basically the thickness ratio of the insulation. So what we are trying to do from the beginning is, I have certain amount of insulation and I'm trying to distribute it to two surfaces. The question is, what is the ratio in which I have to distribute the insulation across two surfaces, hot and one hotter and one less hotter. Now, using one way, I found this one, assuming that both are equal weightage. Using a different way, I found this ratio. The question now is, which thickness ratio is higher? So basically what this asks is, okay, which of these two cases will the hotter furnace get a thicker insulation? Both are same, na? Or what is it? How do you know which is higher? You can just do mathematically, right? You can just put TH by TL and then divide it with the other one and see whether that quantity is greater than or less than 1. If I do that, what will I get? So it will be TL minus T naught. So is this quantity greater or less than 1? So TH is greater than, yeah, TH is, yeah, but basically you can see the expression on I have written here, right? So it will be basically like this, square root of TL minus T naught times TL by TH minus T naught times TH. And we know TH is greater than TL, which means the numerator is less than denominator. So this will be less than 1, which is what our intuition says also. So if you recollect, basically when we try to minimize just the heat transfer, now what we are saying is you have to give more weightage to the hotter one compared to the cooler one, which means you have to give thicker insulation here, because I don't want any heat to get lost from here. So as much as possible, I'll try to reduce the heat here, which means TH will be higher than TL. So in the second approach, when you give a higher weightage to Q, you will get a thicker insulation here. Even intuitively, you can get the same thing. Even from the expressions that you got, that is what it's saying. From the seventh problem to eighth problem, if I take the ratio that is less than 1, which means the second case, eighth is higher. Is that clear? Yeah, so previously, if you consider this, if you just consider this scenario, I have a certain ratio of TH and TL. When I give equal importance to both the hot and the cool one, but now hot and less hot one. But now when we say that here, if I lose 1 watt, it is much higher value than this one, which means I have to reduce the heat losses here compared to this one. Like the insulation, in order to reduce the heat losses more, I have to give a thicker insulation here compared to this one, which means the TH by TL calculated from in this particular way will be lesser compared to the different way. Because in the second way, when I give more weightage to this, I'll have a thicker insulation here, so the numerator will increase. that clear? Okay. And then, yeah, this is the last problem. It's from the boundary layer theory. Now let's imagine, okay, I have not one plate, but I have two plates. And I have two surfaces, and I have u naught is the velocity here. And this is my region of interest, whatever is in this box. So now from the previous boundary layer equation, in the case of a flat plate, I told dp by dx equal to 0 because u is constant and stuff. So is that valid in this particular scenario? When I have two plates also, instead of one plate, if I have two plates. Yeah, so yeah, so in the previous case, when we derived the boundary layer equation for a flat plate, I told that dp dx equal to 0. Now instead of one plate, let's say I have two plates like the one shown here. So what will happen to that particular term? This term, 1 by rho dp dx. If you recall the boundary layer equation, so we have u times d del x plus v times del u del y equal to minus 1 by rho dp dx plus mu times del square u del y square. This is my boundary layer equation, the momentum equation. So in this equation, in for a flat plate, I told dp this particular term goes to 0 for a flat plate. So now let's say I have two plates like this. So what happens in that scenario? Can I still use that assumption? Why or why not? Okay. So in case of a flat plate, why did I say dp by dx equal to 0? Like why did we conclude that dp by dx equal to 0? So we said for a flat plate, we have the Bernoulli's equation which says p plus half rho u square equal to constant. And because u is constant, we said dp by dx, because this term is constant, plus 0 equal to 0. So this dp by dx equal to 0. But if you see in this scenario, what is happening is here the boundary layer comes, here the u naught is going. So if this particular point is 1, and let's take a point here as 2. So at particular point, let's say this is 0 and this is 1. At point 1 it is u naught, at point 2 it is u1. This is 0 and this is 1. So p naught plus half rho u naught square should be p1 plus half rho u1 square. So only if u naught and u1 are same, then we can assume that dp by dx is 0. The question now is that assumption valid? If you kind of imagine, so this is the boundary layer thickness. So if you recall the definition, according to the boundary layer thickness, here the velocity will be 0 because near the surface it should be 0 and should keep on increasing. Here it should be 99% of u naught. So basically you can consider u1. Here it will be 0, here it will be u1. Throughout this it will be u1. Here it will again be reducing, 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 and it will go to 0. Right? Yeah, so what will happen is if you apply the continuity, like u naught times the total h should be equal to u1 times h minus 2 times delta, so which means u1 equals to u naught times h by h minus 2 delta. And if this delta is a function of x, because delta keeps on changing if you move from x, then u1 is not constant. Because u1 equal to u of x, which means if you apply the Bernoulli's equation, then p will be p of x. So now if I apply the Bernoulli's equation, so that means p plus half times rho u naught h by h minus 2 delta square equal to constant. So from this you can take the derivative. So 1 by rho dp dx equal to t dx of half u naught square by 2 h square by h minus 2 delta square. Have to just take the derivative. So to be u naught square. Okay, I'll leave the derivative part for now. We're almost up to time. 7 o'clock is still ending. So I think you can do the derivative here. So this particular derivative here is what this particular term will be, and that is what will go in here. Is that clear? Yeah. We are almost closing the session. So this is the last problem for this week. You have any other questions? Yeah, these are shared already. Yeah, these are shared in the course. There will be something called problem solving session at the end of week 3 or whatever is the last week. If you click on that, you will be directed to a Google Sheet where you will find the recording of this. The whatever we have this session, this will be recorded and uploaded on YouTube. So that link will be there, and all the whatever I have written, these notes also will be shared in a Google Drive folder. You can find both these things in the problem solving section inside the course itself. Yeah, that would be better. Yeah, then we can have better like you'll have more doubts or something and we can discuss them also. Yeah, then we'll conclude the session. Yeah, sorry. It's same on every Saturday 5 o'clock, 5 to 7. You have anything else? Okay, then we'll conclude the session. Thank you for joining. We'll meet next week then.